So just to give a quick fly through of what I'll be talking about today, just a general introduction, just remind everyone who knows us and hopefully anyone who doesn't know us who Farron Technology are, a very brief overview of millimeter wave technology in general and the applications that are therein, including backhaul, Wi-Fi, and again looking in the millimeter wave area for these guys, talking about test solutions for measuring these devices, and then a general summary. So Farron, who is Farron? I suppose they were formed in 1978 from University College Cork, professors developing millimeter wave diodes. It grew as a company to 2005 when we were acquired by Smiths Detection, which was part of the Smiths Group. Their main interest was a passive imaging camera that was being developed called TADAR, and also they spun out Farron then to stand alone as a components millimeter wave test equipment company. Farron itself was transferred into the Smiths Interconnect Group. As part of that, they have a big millimeter wave microwave group in Smiths. In 2013, then the opportunity came up for a management buyout, which was initiated in Farron, and as of October 2013, the company is now 100% owned and operated by the Farron management team. So we're now a standalone, I suppose, being part of a big Smiths group with, as it says above, 4 to 5 billion euro annual turnover, a 10 to 15 person company doing slightly lower percentage than 4 billion. We weren't a big part of their business, so it made sense for us to spin back out into a standalone again. So Farron in general, we have over 100 years of combined millimeter wave experience in design and production and test. Greater than 22 years of millimeter wave design experience, 48 years of production test. A lot of that can be attributed to one guy, I suppose, who's there since day one, but he's the lifeblood of the company. And we have a very experienced millimeter wave CAD department as well. So it is taking the designs that the engineers come up with and putting it into a manufacturable unit, and it's non-trivial. So the CAD side really does have a huge part in our company. And in general, we operate from 30 gigs to 3 terahertz. The terahertz, I suppose, is more based on a historical whisker contact diodes and corner cube mixers. They're a legacy product that we still support to a certain extent, but we wouldn't see it as our key area. It's in 30 to 500 gigahertz based on planar diodes and that area that we're mostly working in. So millimeter wave in general, in the past 3 decades, thanks to as I said, the brilliant presentation from Ian, there has been extensive research and development in millimeter wave technology, and it is starting to show a corresponding growth in customer demand for components and systems. I could go into more details, but I think I'd just be repeating a lot of what was already said. And with that in mind, there's a large number of test solutions available, from signal generators, spectrum analyzers, network analyzers, the list goes on. And what we're seeing now is there's a big increase in demand for test equipment in the V, E, and going up into W and higher band, but most of the commercial interest, we'll say, as opposed to university interests, are happening in V and E band and a little bit in W band. One of the main areas that we're seeing is in backhaul. They're predicting that by 2020, high-capacity base stations will typically, not just exceptionally, but typically require 1 gigabit. Mobile broadband, LTE, which is 4G, LTE advanced, 5G, it will be more widely deployed. And mobile broadband networks will need to evolve to satisfy these demands. And I've a short list of what could be many of all these companies that are involved in the mobile broadband side of it: Ericsson, Alcatel-Lucent, Huawei, Qualcomm. It goes on, but it's an area that is growing. And then LAN and WiGig specifically, so for the adoption of multi-gigabit speed for wireless communications over the very nicely unlicensed 60 gig frequency band. And again, the list of companies interested and looking and trying to promote that is long and is growing. So just a general overview on the backhaul areas. So, and where we're looking at is there's 5 main bands that are for millimeter wave backhaul, offering in total almost 40 gigahertz of bandwidth. You have your low frequency, as we would call, 6 to 13 gig range. So they're great for long range. They'll continue to be popular and grow. Capacity limitations are there due to the narrow channels, but due to all these clever techniques that have been developed, the need to move up from these frequencies has been slower than would have possibly been expected. 15 to 23 gigs would be the most widely used bands globally and will continue to be so going forward. Currently, 38 gigs is utilized quite widely in Europe with wider channels, allowing for gigabit capacities, which is difficult for the 2 lower bands. I suppose, again, I could go into a lot more detail, but it isn't really the area that I'm trying to focus on. Where I'm really looking at is in V-band, which is ideal for the small cell backhaul, high capacity, high repeatability. It has high capacity from its wide channels, high repeatability, as was shown due to the interference from oxygen attenuation. And in backhaul terms, the more likely version would be your 70, 80 gig one, 71, 76, 81 to 86. You have that broad capacity and you have a bit more range than the 60 gig one. So from a backhaul point of view, it's probably a little bit more suitable. In terms of local area networks and specifically WiGig, in layman's terms, microwave Wi-Fi, it's aimed really at the super fast upload and download for someone near a router, so in a single room, more complementary to a house Wi-Fi rather than supplanting a Wi-Fi, but it is aimed at supporting multiple gigabit data rates. Why? As was shown again, gaming will probably be one of the big drivers, high def cameras and TVs for streaming, and these new 4K televisions that are coming out, and just I suppose the cosmetic effect of not having wires and cables running around your house. People are willing to pay for their house to look good now these days, so if it can be done without having to pre-wire and stuff like that, it's getting more and more attractive. Generally looking at WiGig and that spectrum, there's the, as it's quoted, 57 to 65, but the actual band that it fully operates, allowing for the envelopes, goes from 55 to 67 in reality, for the 4 channels that are utilized. I started messing with some graphics and tried to implement some stuff in my limited experience with PowerPoint, but it's just an example of the channels and as they sit, from a design of the test technology point of view. It really is you're trying to get the optimum performance just in these 4 channels, where linearity, flatness of your gain or your transmit power is what's critical from a test and measurement point of view, because the flatness of your up and down converter systems, which I will get to in a few slides, allows for your ease of calibration. If you have a lot of ripples in your transmitters and receivers, or up converters and down converters, then you'll get errors in when you do calibrate it out at a baseband level. So they're the four main channels, and with that in mind, Farron looks at what can we do to allow people to test and do measurements at in those frequencies. So historically, S-parameter characterization at RF and microwave frequencies are readily available. Most VNAs on the market, high frequency VNAs, are through frequency extension products. Farron supplies these types of solution frequency extension products. Seeing as my sales and marketing manager is below, I'll just repeat, Farron supplies these solutions for frequency extension products. And due to the increased interest in these 60 gigs links and 71, 76, 81 E and V band, we're seeing an increased interest in how best to characterize and test these devices and links. And it's not just, I suppose we know we'll never be a company making these small chips that are sold in the millions and thousands and hundreds of thousands, but we are interested in being a supplier of the test equipment for these types of components. So one of the first projects we developed was an FCE15 system for communication link extension. It's built on working with arbitrary waveform generators, driving an up converter chain, external signal generator, giving an LO that can allow for user controlled, and then a low noise receiver on the down converter side that can be used with a suitable oscilloscope. So it's taking your baseband equipment and just allowing the same level of functionality to be done at higher frequencies. So the first unit that I'm showing here was the up converter that we made. The challenges that come with it is your operating bandwidth. As I said, 57 to 65, give or take. Your transmitter P1dB/linearity is your main area for your up converter. Your spectral purity, because any spectral issues will feed back into your QAM or your whatever signal you're transmitting. And as I said, that in-band flatness. So looking at the up converter that we did to achieve the operating bandwidth, we went with using dual up conversion so that we could achieve sideband filtering to avoid contamination of the signal with single sidebands filtering. So what we were taking was a 6 gig IQ signal from an AWG and up converting it with an internal phase locked PLDRO that gave us an intermediate IF at roughly 16 gigahertz, and then taking the external LO and multiplying it up by 4 into another mixer. It allowed us for that bandwidth that we required without issues with sideband contamination, and with the right levels of filtering we were able to avoid any spectrum issues. There are other architectures, which I suppose this was the first demo model that we decided to build to show what we could and couldn't do at 60 gigahertz. On the back of that, we've spoken with other customers and come up with some slightly different architectures that suited specific needs, and to find that balance really is what we were trying to do. And as I said, to achieve those various challenges, we had to look at dual up conversion, a custom designed power amplifier to achieve the output P1dB and the linearity. A lot of effort was put into the filtering and design of the filters to ensure that we got as good a spectral purity as we could, and also then careful S-parameter matching of the individual components with isolators and that to make sure that we had good in-band flatness on gain. Similar for the down converter, slightly simpler architecture because the level of filtering needed and the spectral purity wasn't quite as big an issue because you were able to direct down convert because you're receiving the signal, so we didn't have to worry about sideband filtering. But again, the operating bandwidth was critical, so using broadband components, but not quite as tricky as the up converter. Sensitivity wise, again, it's using as high a spec low noise amplifier as we could make to ensure that we were able to get as good a RF performance as possible. Filtering, and again, the careful matching of the S parameters as well. So where did we see these units being used? Well, I suppose there was two potential applications, and that's what we found from talking to most of our customers, that either the units would be used as golden transceivers, i.e. you calibrate your system and then substitute for a transmitter or a receiver to measure the relative performance of your own system, or else by using the combination of the up and down converter, it allows you to characterize antennas, components, and some subsystems as well. And mainly because I didn't want to repeat too much of what Ian was saying, I'm getting close to the end of my presentation. Managed to, Helen's smiling because I've allowed her to pick up some of the time that we had probably lost. But again, Ian had definitely covered a lot of what I could have just repeated, but I think he said it a bit more eloquently than I would have been saying. Here is just an example of one of the systems we built, which was, so you're looking at an AWG, in this case it's sitting on Keysight equipment, so a Keysight AWG running MATLAB, which itself controls the oscilloscope as well. It's transmitting 16 QAM, it's not very clear in the picture, 16 QAM IQ signal into the up converter, where it's up converted, and in this case it's at the channel 4, which is about 65 gigahertz roughly, transmitting, being received here by the down converter. We have two separate LO sources, one for the up converter and one for the down converter, and the output of that is going straight into the oscilloscope. It isn't very clear in the picture, but seeing as I have managed to get ahead, I have a small video of it running there. So. Hello, my name is Michael Crowley. I'm a principal engineer at Farm Technology, and I'm here today to introduce our new 60 gig communication link extension system. The system consists of an up converter and a down converter to simulate any standard 60 gigs communications. The up converter takes an externally supplied local oscillator from any standard 20 gigs low phase noise signal generator and conditions it and mixes it with an IQ signal to transmit from 57 to 66 gigahertz, and the receiver then can receive that signal again in the same band, 57 to 66, and down convert it again using an externally supplied local oscillator from any standard 20 gig signal generator to an IF signal that can then be analysed by a standard oscilloscope with the relevant software for analysing communication systems. In this example, we're using an Keysight M8190A arbitrary waveform generator to supply a very standard 16 QAM IQ signal on a 6 gigahertz carrier that is being fed into the IF input of the up converter, which goes through a dual stage of up conversion to allow for sideband filtering and various signal conditioning to be transmitted. This system has a P1dB of roughly 20 dBm, so there's a wide bandwidth of power operation where you'll be able to operate in the linear band of the system. That's then in this demonstration being transmitted at 65 gigahertz, and we have a receiver at 65. The receiver then takes the 65 gig signal and mixes it through a low noise amp with 60 gig LO, which is supplied by a 15 gig LO input, and it's conditioned multiplied by 4 internally to give a 5 gigahertz output, which is then in turn analysed using a DSA-X from Keysight running the VSA 89600 software, which is showing a very good cluster of 16 QAM with an error vector magnitude of roughly 3 to 4%, on the basis of the IQ signal being input to the unit with an error vector magnitude of roughly 1%. And just to show that we are actually transmitting a 65 gigahertz source or signal. Thank you for your attention. So that was just a very quick demo of the, I suppose, our own demo that we created to, I suppose, prove to ourselves that we could build a system, but it might not necessarily be exactly what certain customers would want, but it is the conversation starter so that we can sit down and talk with companies and see what exactly they want or they require in terms of test and measurement at these frequencies.
Thank you very much. Thanks, and congratulations for getting the time spot on. Does anyone have any questions?
I'd be interested in your view about how you think devices like this will actually be tested.
I suppose it is a tricky one. We were looking at developing this system and we were trying to figure out a kind of chicken and egg situation. Do we try and drive a customer to how they want to test it, or do we sit down with the customer and see what they need testing? Where we have seen a bit more traction is in an integrated version of what we've kind of demoed there, where you've the up and down converter in a single unit with switchability and the ability then to use it as a standalone up converter or as a standalone down converter or as a system, so that you can measure an antenna that might be attached to the system. So it's what we've kind of seen from kind of getting that demo out there and talking to people is that, yeah, it's of interest, but we need more than just 2 units sitting there. There needs to be a bit more controllability, a bit of switching that you can calibrate more easily, stuff like that, you know. Okay.
Just one more.
Oh, sorry.
Yeah.
Yep, sorry.
What is the power of the
In the demo we had there, we were using a system that has an output of P1 dB of roughly about 21 dBm, but since that video was made, we now have a unit that's giving 25, 26 dBm P1 dB at full band 57 to 67 roughly gigahertz.
Great. Thank you very much, Michael.